Swayam Prabha. Digital India. Educated India.
There is no place you can give W1, W2 in NSGA2. We haven't talked about. Or NSGA2 or which one? A priori approach. In this case, you are not going to find anything here. So you are going to find from here to there and maybe some points here. So this point will be unfounded, no matter what weight you use.
So if you use EMO also,
no, EMO doesn't require W1, W2. EMO you will find a good distribution because we don't use any weighted sum. We only use domination check. So as long as the 2 points are non-dominated and there is no other point close to it, you are going to find it eventually. So we don't combine objectives in any EMO method. That has to be absolutely clear, right? That this difference. So that's the reason why we are moving into EMO. More and more people are moving into EMO. That it doesn't use those weighting and or any other way to scalarize. So it keeps the objectives separate, and that's why we can discover the entire Pareto set. But here we are talking about something else. Here we are talking about we've done the EMO or point based method and we have generated a lot of points. Now we are picking. So how do we pick? So this way of doing it is, okay, let me first assign a pseudo weight because this gives us an idea of the importance of each of the objectives, and then I have some target weight in mind and I go and see which one is close to that, and that's the point I pick. No, there again you don't need weight. Here you ask decision maker for these reference points, and these are not weights, these are objective combinations. Like I said, this is cost and this is emission level, pollutant level. You are saying I want to spend, let's say, $1,000 and I want 60% removal of my pollution. That's my wish. Okay, turns out no, I cannot give you a solution because any gray point would be a solution I can give you, but then I give you something that is close to you, close to what you are looking for. So how do I find these? Each of them is the RNSGA2 way. There is no weighting again, you see here. Okay. Again, this is a concave one. So again, the weight idea will not work. If you do weighted sum, you are only going to get this point and that point, nothing in between. Okay. But with the RNSGA2, you can find these points, and now not the entire thing. If you do NSGA2, you are going to find the entire thing. But with RNSGA2, you only find these 3 patches close to each of your reference points. Okay. All right. So these are some a posteriori way of doing it. Last one I'm going to talk about is interactive, but this is just one idea of interactive I'm going to give you. A lot of people have started to work since our paper from 2010. So what is it? Both these cases you saw, first we did decision making and then optimization in a priori. A posteriori we did optimization, find a bunch of points and then make decision. Here we're going to do it in combination. So here's the principle. We run maybe an EMO starting with random points. We run EMO, let's say, for 20 iterations, 20 generations, and we get 3, 4, 5 points. Maybe we got 50 points, but we just pick from it by some clustering method 4 or 5 points solutions and go to the decision makers and show them pairwise, 1 with 2, maybe 1 with 3, maybe 2 with 4, like that. Pairwise we show them and say, here are 2 solutions we have found so far with a trade-off, because they will have trade-off. Trade-off means from 1, if I show them 1 and 2, going from 1 to 2, maybe I have worsened my F1, but I got a benefit on F2. So that kind of trade-off, and the decision makers can see that. So we show them pairwise instead of all 5 of them simultaneously. So we tell them, here is one solution, here is second solution. Which one do you like? Let them use their own judgment of preferences and all that, and they take a bit of time, let's say, and then say, yeah, I like 1. Okay. Then we come back and say, here are 2 other solutions. Which one do you like? And they say that one. and at some point they say, go away from my office, I don't want to see you anymore, I don't have time. Okay, even if you got 1, 2, 3 of such things is fine. Okay, now you go to your office and try to model the decision maker. A terrible thing to say, but mathematically you try to understand what was the preferences that the decision maker was using. Okay, so this is what we're going to discuss next. So we modeled the decision maker in this paper, but later on we did some other more complicated things, but you could come here and contribute. This was our function for modeling the decision maker. We called it the utility function. These are now not functions of x, this is functions of the objective values. If I have two objective function, I'm basically thinking of a contour of these function here. So you see there are 4 unknowns in this function. From this information the decision maker is provided, I am going to estimate what are these k1, k2, l1, l2 values. Now if you use another value function, you will have another set of parameters and all that. How do we do that? Okay, here is the algorithm. So we went to the decision. So let's take an example. Let's say these are 5 solutions, 1, 2, 3, 4 and 5. Forget these lines that you see, I should have shown in an animation way. But these 4 solutions, I've run a NSGA2 for few generations. My Pareto fund can be still here, I have not gone there yet, I am here now at this intermediate generation. And there are lots of points here, I've clustered them and I've picked 4 points from it and I'm going to the decision maker. First I am asking decision maker showing 1 and 2, 1 and 2, and I'm saying can you say which one is better? Let's say in this perfect case, I have done all 5 choose 2 pairs. So that means 5 times 4, so 10. All 10 comparisons the decision maker had the time and told me 1 is better than 2, 2 is better than 3, 3 is better than 4, 4 is better than 5. This is how he told us. Okay, now I come and formulate this problem. Every time when I gave him I and j, and he said I is better than j, I put a constraint saying that value function that I showed you, value function when I put the corresponding f1, f2 for ith point minus the value function value for the jth point, their difference have to be at least some positive value bigger than or equal to epsilon. What is the epsilon? I try to maximize that. So I'm saying when I is better than j, the value function at I and the value function at j, their difference have to be as large as possible. That's how I'm clearly saying why I like I, because this underlying value function he's using, in that function I has a much bigger value than j. Any cases he's saying, oh, I cannot say which is better. It can usually happen when they're far away, like this one and this one if you compare, or they are so far away, you see, this one is best for f2, almost very close to minimum of f2 but worse in f1. This one is very close to f1's minimum but not so good in f2. When you have such diverse, decision makers usually cannot say which one I like unless they have a very clear cut preference for one of the objectives. So they might say, no, in this case I cannot tell you which one is better. Okay, fine, it's fine. Then you say, okay, the difference between the two value functions, absolute, because I don't know which one is better, has to be at least, we put here actually 0.1 times epsilon. This delta v you can decide which one, we did 10% of epsilon. So now that so I want the difference to be not differentiable that much. So I basically say 1/10 of this decision I'm going to put it over here and it should be less than equal to that. So when they are equivalent, right? So for all the pairs I can create these two, and the way I have created this, it already satisfies this increasingness of the function and v has to be non-negative and all that are done. So if you solve this problem for the given decisions, you will get an epsilon, you will get the variable here are k1, k2, l1, l2, right? So an epsilon. So you are going to get a value of all of these and then you can plot this value function of each of these points, and I have done that for the optimum value of this. And higher you go up here is higher v value. You see that rank 1 is at a higher v than rank 2 because it's slightly lower, right? And then rank 3, then it passes through rank 4, and then finally passes through rank 5. So I was able to find a value function with K1, K2, L1, L2 that honors all the 10 decisions that decision maker has given us. That means according to this value function, if the decision maker had given me the options rather than thinking, I would have gotten the same outcome. Does that make sense? So I've actually got additional information about how to combine F1, F2. How can I utilize this now for next 10 or 20 generations of an SGA2? That's the big question. So we got the value function generated. Oh, here's another example where I said that actually F4 and F5 I cannot differentiate. Now you see the value function changes. And I have P1 better than P2, P2 better than P3, P3 better than P4 and P5, but P4 and P5 I cannot differentiate. So you see the two lines passing through P3 and P5, P4 and P5 are very, very close to each other. Not always it's possible, but if it's not possible, you have to go back to the decision maker and say, you have been inconsistent. Don't say that, but in your mind you know that this is what he has been. So you say, can you revise one of your decisions? Because I am not getting a good value function with what you said. Because they're human beings, okay? They are not thinking of a math function when they're doing. So there could be some inconsistencies. So you try to clarify it. Or if they cannot, then you have to ignore the ones you think are most affecting your calculation. So you can ignore that. Okay, now how do you utilize it? There are several ways you utilize this. First is, I got the value function, and let's say here is my F1, F2 space, here is my Pareto set. So from the value function point, I can, so one of the points in the value function, so if these are my current Pareto points, I actually take the, one of the points I can decide whichever way, using some ASF or whatever I can decide. And at that point, I can find the gradient of the value function and then make a search along that direction to say where is the optima along that line. So if the Pareto front is here, this will be the optima. This gives you an idea of how much still you have to converge. So it can give you an idea of the convergence before you terminate. So this can be used as a termination condition. The other way you can use is redefine your domination check. So for maximization, B is going to dominate this part. It's a maximization problem. So over here, everything is worse than B because your maximization means you want to go in this direction, right? But now with this value function, you can actually add that value function and say this part will also get dominated by B. This part will also get dominated by B in addition to this. Simply because this line says as you are moving up like this, you have a better value functions. Below this, you have less. So these points are already below to this line. So you say these are worse. So your new definition of domination becomes this line, and this. Remember I talked about generalized domination. Now this is your generalized definition of domination. So every 10 generations, 20 generations, when you are going to the decision maker, you are actually redefining your domination. Part of it is based on Pareto concept and part of it is based on these decision making concept. So with that, we've done some simulations. Here is the entire Pareto set, but when you come, like you come from here, you see there are 5 solutions every time, but we have to go to, in this case, decision maker 70 times. But of course, decision makers will not have that much time. You'll probably go 3 or 4 times maximum. So you need to increase the gap in between, but this is to show that you start from here and the P1 is always chosen. These are always chosen, and you see eventually you come and converge to one part of that Pareto set. You are not finding the entire Pareto set and then making a decision. You started with the whole set, whole wide space here, and then you are kind of narrowing down. Who is helping you do that? Why not here? Why here? It's the decision maker's decisions are allowing you to go to the right place. So these are much faster in terms of computational time, but overall time going to the decision maker, getting information may be time consuming. But at least the computation time is less, and you are not unnecessarily finding the points that you will not be choosing at the end, right? Any question? So this is just a framework. You could change a lot of things here, the value function. You can also change the ways we are utilizing this to many other ways and things like that. Yeah, this we done in 2010, long time ago. I need to do more stuff here, going back and see what other things are possible. There are some more follow-up stuff we did, but let's forget that. Okay, so you got to see a priori where decision making was done, and then just go and find the resulting point on the Pareto set, or a posteriori where you don't do decision making, you just find the entire Pareto set and then use decision makers preferences to pick one, trade-off, pseudo weight, distance, whatever. Okay. And then the last one we saw briefly is the interactive method. Those are optimization, decision making together. Okay, now oftentimes this last method I'm going to talk about also utilize a lot. It's called analytical hierarchical process. By the way, in the evening to after in the today's homework, what you're going to do is we're going to do first the NSGA2 optimization, finding the entire Pareto set. We'll do a posteriori exercise, and then I asked you to do two different methods. One is the pseudo weight, the other is the trade-off. Both these methods you're going to use and find a solution for out of maybe 100 solutions. Pick a solution. So we'll do that exercise. And then the second question is using analytical hierarchy process. So this is more like a group decision making. This method, as I yesterday mentioned, very popularly used in high level decision making. So it's good to know. But there's an unfortunate part here is that this is only applicable when you have very, very few alternate solutions, like maximum 5. So if you have 100 solutions, 10 solutions, you would not be able to use this. So this is more like a selection problem. You have already chosen, like in the previous case, I have chosen 5. The decision maker could have used AHP to pick one and say this one is better than that. I mean, for 2 you can use this, but 2 there are much other methods to use. So when you use like 3 to 5, you basically use this method. Number of objectives also should not be like 10 plus. Then there are too many experiments you have to do. So usually 4 or 5 objectives, 3 to 5 solutions, you should think of this method. And you have that many solutions, you have to pick one. Decision makers are still involved. Okay, their preferences are still involved. So here is an example. Let's say I show it with an example problem. This I have taken from internet. Let's say I am trying to choose a suitable leader for a company. Okay, and I have 4 different criteria for choosing that person. What is their experience level? Are they young or they have got a lot of experience? What is their education level? What is their charisma when they speak, when they talk? What kind of authority, or do I like, is it charming or not? So that's important at that level, right? What is their age? So these two can be related, but sometimes a young person can have a lot of experience as well. So these are the 4 things, let's say, I'm considering in order to pick a leader. And I have 3 options, Tom, Dick and Harry. Okay, these are it's an artificial problem. Which one shall I pick? That's the question. So you see very few options, alternate solutions, about 4 criteria. What's the one I'm going to pick? So that's where you think of AHP. First thing you do is look into each of these solutions, like in this case I have Tom or Dick or Harry, with respect to every criteria independently. So I'm looking at first the experience criteria, and I'm comparing these 3 people, 3 solutions with respect to that. When I'm doing this, I'm not going to think of age, I'm not going to think of their education or any other criteria that I have in mind. Okay. So now I need some decision makers. So let's say I'm running this AHP, but who is going to make this decision? Probably the committee members, who is going to the selection committee, which will have maybe some senior people from the company with a lot of experience, who has direct stakeholder, maybe some stakeholders. It's a leader of a company, maybe it serves some people, some governmental offices, so some representative from there. So you decide on that committee, they come, and you do it this way. You say first we are going to look at only experience, don't think of anything else. Can you compare pairwise Tom with Dick and say which one you think have more experience? Okay, then you look at their biodata, what they have done in their life, and then you say something, another person says something. If there is an agreement, great. And sometimes there is no agreement, then you do voting. There are a lot of group decision making strategies you apply, but the goal here is all of you together have to come up with one number for each of these pairs. So if you say they are equally important, they are equally good, then you put a 1. So Tom with Tom is of course 1, but Tom with Dick, so he says Dick is 4 times more experienced than Tom. They collectively came up with 4 will come something in between, moderately important to strong important. See, the number is getting higher if you think one way or the other more strongly. You think Dick is really very experienced compared to Tom, then you put 9, maximum 9. So it's 1 to 9 scale. So here if you put 4, you put 1 over 4 here, because if Dick is 4 times more important than Tom, Tom is 1/4 times important than Dick. Does that make sense? So you fill all this up, diagonals are going to be 1 because the same with the same. You got a matrix, symmetric matrix. What do you do with it? The next one says you come up with some priority values. How do you come up with from this matrix? Okay, I looked hard. Sometimes they don't say it, but in some places I found, as if it's very common thing to do, but I found and created a MATLAB code for what the method they use. So you provide the matrix like this. Okay, I don't know why it is. This is going to be semicolon here, and this is semicolon. So basically there are 3 by 3 matrix here because of the 3 choices you have. Number of is 3, then you follow this process, and it's going to give you the C value. This C, so there are 2 ways of doing it. One set of papers use this geometric mean idea. Another one use the arithmetic mean approach. So I guess I'm saying you to use the arithmetic mean. So I've commented the geometry. You can use both and maybe take an average, but you do the arithmetic mean. So eventually you get a C. Sorry, where did I finish? I have to finish here. So C I have to compute. Why don't I have one second? Where is my C on the arithmetic mean? No, I think this should not be commented. So C is common for both. So once we get the D and the B, you compute C. D is probably for that one. Anyway, we are going to just uncomment this. Okay. So you get C. So once you get C, this is a vector you get, and that vector actually goes over there. Okay. There is a CR value they compute, that's called the consistency ratio. All these numbers that they have given, does this mean, and is this consistent or not, or you have contradicted? Okay. For example, you said Dick is better than Tom, and here you said Dick is, let's say, also better than Harry, but somewhere you said Harry is not better than Tom or something. If you have 3 by 3, maybe it's not possible, but when you do higher number, you may have contradicted, right? So that ratio will come here, the CR value that you compute. If this is less than 0.1, then they say they are, you will say it will okay, and what's the, if it's okay, then you go and put that number here. If it's okay, you ask them to redo this. Okay, you got the priority value, store it. Actually their sum has to be 1. Repeat the process for others. Education, only thinking of education, again find the priority. Age, priority. Charisma, priority, and save them. Does that make sense? So if there are 5, these values are compared with RCI, and these are given in the literature. I have not completely understood this, but they go back to some other papers, even that's not understood how they get these values, but I think it comes from some statistical analysis process. If you really want to understand, then you have to go back many years, because these are kind of following up from many years of literature. But here I made it simple for you, just put them all into this so that you can, in the, when you do the exercise today, you can actually use these values. Okay. Next thing you do is take all the criteria. Now you forget the solutions. You forget who is Tom, Harry and Dick and their CV. Basically you do this, this one, I mean. You now have 4 by 4 matrix with experience, with education. According to you, being a decision maker, is experience more important for this position or education? experience versus charisma, experience versus age, and all these 4x4 things over here. Because now you are judging these criteria, which one is more important. It's sort of like the weights that we are talking about. But these are not weights, these are basically pairwise comparison. So he said, the group together said, experience is 4 times important than education. Experience is 3 times more important than charisma, 7 times more important than it. So experience seems to be the most important thing here. And the respective one you put 1 over, right, on that symmetry. Once you got that, you have to go and put n equal to 4 and give this 4x4 matrix here, and it's going to give you this priority. Put them up, and their sum will be 1. Make sense? This you have to do only once. Okay. So now if there are 3 solutions, you did 3 of those before, and now it's 1 for the criteria. Now you are ready to do this big table. Make this big table where you say 4 different criteria, each of them has 3 solutions. So this experience, the priority value comes from here, 0.547, you put it over here. And then for experience, for Tom, these 3 numbers come from here, 0.217, 717, 0.066. Okay. Then you multiply these 2, put it here, multiply this with that, put it here, and multiply this with that and put it here. Their sum has to be this, because their sum is 1. So since you multiply, this has to be this. Now you go to education, get the number from here, this 4x4 thing, and repeat the process. These values are coming from the education part of it, okay, that we did before. So like that you do this cross product, the products of all of them. Once you've done that, now you make this, each of these 3 candidates, Tom, you pick this number, you pick that number for Tom, you pick this number for Tom. For every criteria, you pick them up, add them, and you get the goal. Similarly for Dick, add them, for Harry, add them, and there has to be 1, and see which one has the highest. So he is the winner. Okay, if you now go back and see Dick, why Dick is the winner, you can see he's 4 times more experience, 9 times more experience than Harry. If you do the other one, age wise, maybe he's not that good, okay. But here again, Dick with respect to Harry in charisma 4 times, but Tom has the most charisma, but age wise, he's kind of intermediate. No, he's, yeah, intermediate. So I think overall, by looking at this, maybe difficult to say Dick is the winner, but since you went through these decision makers' preferences and they were the people who driven it, you as a optimization person didn't do it, right? You just driven the whole thing, but they had controlled everything. So it's using again preference information of the decision makers, but systematically finding out a number. When you come to this level and you declare Dick is the winner, some people will say, I don't like, because that person may have thought another solution would have been better and it didn't satisfy. Now they start to complain, this method is not good, somebody cheated, and all these things happens. Before you announce this, you have to say, anybody has any last word? Because after I show this, you will not have anything to say. So they can say, yeah, I want to change my thing, and okay, you go back and change and revise it and come back. But before this stage, they say clearly, you should make sure everybody has nothing else to contribute, and then they have to be quiet. Whatever solution they get, they got to be happy because they're all driven towards it, right? There is no cheating here. And there is some science here, except that the choice, the selection that's given, that was subjective. So this is one way I thought we can utilize when we are narrowed down to 4 or 5 options with maybe 13, 14 even objectives, and we have actually done that. So let me take the next few minutes to show you this example, which is called wicked problem solving. I don't know whether you've heard this word in the context of problem solving as wicked versus tame. Most practical problems these days fall into this category of wicked. Some government level, like Australia, I know, US haven't done that yet. I think China has done now. They have declared lots of problems from practice which fall into this category. And there are lots of characteristics a problem got to have before you put this. one of the thing is there is no one clear answer. Okay. Second is the problem is not clearly defined unless you give an example, because it's such a complex thing you cannot just write a math objective function constraint or anything. You need to give an example. Okay. These things change with time. Okay. The problem doesn't stay constant, and of course they are complex. They come from socio-economic part of the thing. Some problems are, for example, forest management, land use management, obesity problem, educating mass. So these are, societal problems. If you now try to sit and say, okay, what is the objective function? Oh, by the way, another criteria, they clearly say they have to be multi-objective. It cannot have single goal. Okay, any of these I said, you think and say, whoa, this is multifaceted. Lots of different things have to be considered before I solve this problem. So first thing is, at the government level, is to classify such problems, to say, okay, these exist, there's a lot of peculiarities in them, now let's see how to solve them. So ask professors, other parts of the scientific body, of the society, to come up with ideas, right? So Australian government, particularly if you search for WCAD, all you will see is going back to Australia. They have been doing it very, very seriously. So we got this problem from New Zealand, which basically follows Australia. It was a piece of land, quite a bit, I forgot how many acres, maybe I have that information, which is owned by a local tribe there called Maoris, tribes there. So they own this, but part of this, so this is the boundary here, this is a sketch of course, and there is a lake, and that's kind of shared by other people. So that's not their property, but the rest of it is there. But they are doing lot of things to their grasses, like put high nitrogen rich fertilizers so the grasses can grow taller and their dairy is good. But with rainwater, they're all going to the lake, and it's making it unusable. So local people complains that they have health issues, and they complain to the local policymakers like government offices, and the government people realize that's what they're doing. They go and put a notice. You cannot put this, you cannot put that. And these people don't like, because they think government is against them. They are taking their profit away because they don't understand the complexity of the thing. So at that point, I think it was 2009 and 10, around that time, I was just planning to move to MSU, and this professor that I was associated with there was telling me over Zoom that this is what they are discussing with the New Zealand government, and my coming over there is going to be helpful in solving this, because it's a multi-criteria problem. So I got naturally interested in it. So while I was in Kanpur, I was looking at this problem and what they're doing. Fortunately, there's a forest department there who has all these models that how the rainwater goes down to this landscape all the way to the water. If there's so much rainfall, so much of nitrogen will go there, and there are different kind of models are there. So I looked at these models, they're pretty advanced. Some of them are using machine learning even at that point. So they've collected a lot of data and did that. So I thought, well, we have models to optimize. Only problem is there were 14 objectives in this case. By the way, I show you little details, and here is the paper where we wrote all that eventually. But we got a practice prize, Wiley practice prize from the IEEE Society on Machine Learning, MCDM in June 2013 for this work. So here is the real landscape. Here is the lake over this side, and you see these blue ones. Currently they are doing dairy. The blue ones are dairy, means all the sheep and all that are cows, and all these are there. So you see how close they are to the lake. So they are taking proper care of this lawn, and all of these fertilizers are going there, right? There are some hill areas where you can't do anything. Turns out there are 315 paddocks. Each one of them is isolated with a paddock, okay? And now you have to decide in each place, are you going to do what? You are going to do for dairy, you are going to do for bulls, you are going to do some bushes. So there are about 100 options that you could do in each place. So 315 places, 100 options each, and then you cannot change everything in 1 year, because it will be very, very expensive. So they stagger it over 10 years. So this is the entire search space. It's a large number, right? Only 10 to the 82 atoms in the universe, right? So it's a huge number of solutions we are talking about. You can't enumerate everything. Many problems in practice we go to that kind of number. So we need to have a smart algorithm which will look at only a fraction of these solutions and get to a good solution. Need not be optimum, but a good solution that is better than what they have now. But what are the objectives? There are about 14 different objectives. Some of them are related to productivity, like how much saw log, like log from the trees, how much milk, how much other dairy products like butter and all these they are producing, how much profit they are making. So there are several, and then how much loan they are taking, what's the interest rate and things like that. So there are about 14 different objectives. We could put them into 3 classes, productivity, I think environmental effects, and the cost. So these aspects, right? So it's such a complex problem, and you are dealing with decision makers that are heterogeneous. The Maoris, you have to involve anything you do, anything you change, and they are not that educated, and they have a hierarchy in the society. The seniors only make decisions, juniors just work. So we had to meet with the seniors who doesn't understand science that much, who cannot see a graph. So we thought of a virtual reality based system we developed. You see this student is wearing goggles at that time, whatever we had. And these pictures are 3-dimensional Pareto sets. We clustered 14 objectives into 3 clusters, and we are showing them in 3 axes. They can actually go under these, seeing this, and see the difference between 2 points. And if the joystick click one of the points, they see the productivity, cost, and everything coming out there. So we thought this would be a little helpful for them in a life scale kind of graph to see. But those are cosmetic stuff. All the videos don't come very well. But what this was showing is, I think there's a resolution issue here. How that solution I showed you transformed in 10 years to a new optimal design for the most environment friendly solution. Okay, so eventually I'll show you that solution. So this environment friendly solution this is the one I was animating. So you see there are a lot of blue here, right? Now they've all gone. The algorithm decided to take the dairy out from there and put it somewhere hidden, so that whatever they do there is not going to affect the lake. Okay, and we didn't tell that. Algorithm has figured this out. So this is the most environment friendly solution. And then I'm picking, so there are about 100 designs we had, 100 different solutions we had. We did every optimization from MSU, and then we go there with about 20 of them. Now the problem is that they don't see eye to eye. The government people and the Maoris, because there's so much animosity, they don't see eye to eye. They didn't even wanted to sit together. We invited the local Maoris to come. We are waiting, they don't show up. And then we go to their place and say, hey, you didn't show up, but we need to do this. They says, no, we are not going to sit with the government officials. If you have to do anything, come here. I said, okay. We go with our laptop and we show them this design, because this design we know they will not like. Remember my nadir point to ideal point? That same strategy I used there. I learned very quickly. So I said, okay, here is a solution we found. They look at it, look at their profit. I think I said the other way. This one we did with first, right? With the Maoris, because this is the one they will not like. This one doesn't have much profit, but it's good for environment, good for the policymakers. They says, no, this is not going to bring enough money for us to feed our families. So no, we are not going to do this. So I say, okay, don't worry. We'll show them another one towards this direction. Okay, because we can pick, we have 100 solutions. We pick those. Slowly go. At some point they said, okay, we can live with it. We didn't have to come all the way to the highly profitable. But this was part of it which we didn't show them in the beginning. Now we go to the policymakers, government officials, start from here and then go towards that, and we found some common things that they have. Fortunately, there are 4 that we found common between them. Okay, and these are these 4. So this is again the value path or the parallel coordinate plots. 14 objectives, as you see. Each vertical line is an objective, and one line, green line, is one of those 100 solutions, showing the trade-off. These 4, as you see, are the picked ones eventually, that both of them picked. Now we go over them multiple times, show these 4 thinking that maybe they will agree on one common, but no, they were not bulging. They were basically deciding on their best of the four. These people also best of their four, and they are not the same, and we could not convince them. So we said, okay, we have to do AHP, because now we have 4 solutions and then 14 objectives, fine, but we can run AHP and then we can find a solution, and then they cannot say anything. So what we did for AHP is we have 4 stakeholders groups, these Maori landowners who actually own this place, some seniors from there. This was the district, Rotorua district planner, so these are government officials. This is again senior tribal regional planners, they have their own regional planner, and 2 senior forest planners who had developed those models. Each interview took about 1.5 to 2 hours, okay, sitting with them, doing all this AHP business, right? With math, all they have to do, they don't have to look at my table. They just say whether they like this or not, whether getting more wood is more important than getting more milk, so that kind of thing. To district planner, they said, I don't care. So we just put 1 for them. But then we had to come up with one number. So there are some averaging, voting we did to do that. Then we apply the analytical hierarchy process, spelling error, okay, and then we come up with this result. So these are the 4 options we had, and these are the values. This is the highest one. Here we normalized with respect to the highest one. So this is the winner. Third one, which is this solution. The black one over here. You see, slightly different from the other, and that was the winner, and at that point they cannot say anything. Okay, if they say, then we have to start all over again. Okay, so I think this strategy can stay, that you start with astronomically large search space. You need a computer or a good algorithm to get to about 100 good solutions. That's the bull work that's done. Once you've done that, do some manual screening and come up with maybe 4 to 10 different solutions. You have to still sit with them to do this, and if you can make a one get from 100 to 1, great. If not, then you use this AHP concept and pick a winner. So that's the whole thing I'm talking about, and the search is more over here where you can use EMO, then group decision making, and then final choice through AHP. Any quick question? I've just gone through, showed you the overall philosophy what we use there, but there are a lot of details that are in there. This project took us about 2 years to do. Okay, any comment? If not, we move to the next. These are simple things, small things I'm going to show you. Another similar opportunity I had with Finland when I was there, but this work we've done after I've come back because we established some connections. We started talking about it, but by the time the project came, it was a little delayed. They have big forests in Finland, right? And there's a lot of biodiversity, different kinds of trees over there, like with large carbon footprint to different medicinal values to furniture related stuff or building related stuff and everything. So the idea there was that if they don't cut the forest, that means cut the trees, new trees will not grow. You need to have the sunlight to come down, right? So the question is, how do they cut? What do they cut? To what extent? Because there are a lot of different kinds of species of trees, and they know about it. So which to cut? So we have this GA solution you see here. This is over a few months how they would cut. Whenever the black comes, we are saying the cutting schedule, what to cut at that and how much to cut, and then don't cut in the next month, then another one. So this basically shows the whole plan of what they should cut, when they should cut. And you see we made a simulation, and whenever there is this cut, you see it gets depleted a bit, and then again the tree grows. So we have tree growth model, and when we cut, we just take those out, and then again the growth takes place. So we have a model that's running. There are 3 criteria we used. Biodiversity, we want to maintain the biodiversity of the forest. Carbon storage, maximize, and the profit also we want to maximize. So when you do these 3 objectives, you see there we get a Pareto surface, this green one. These are lots of points we found using lot of these RNSGA2 kind of ideas, and then the blue ones, you see some of the blues are there too, is found using NSGA3. which I'm going to talk to you about tomorrow. It's basically an extension of NSGA3. So basically to show that blue is a representative of the green, and then from this we isolate these 5 different solutions which are well dispersed, good for each one of these 3 and some intermediate. We manually pick these solutions, but we cannot still give them 5. We have to give them 1. Now we sit with them and we do the trade-off analysis, like the trade-off analysis I talked about a posteriori with all 5 of them. If you look at the paper, here is shown, it's all discusses that trade-off method and everything. And I think we picked one of them, and that's the one I'm showing you here in the simulation of what's happening. So all these methods that I'm showing is not just I'm telling, we have actually used them in some practical problems. This is the one we are doing now. It's called Chesapeake Bay. It's the east part of US. There are 6 states that are involved. This is the whole bay area. It involves lots of counties and 6 states. And here is the basically every way, all the rivers, estuaries are come here, and all the pollution goes to the Atlantic Ocean. I am deliberately chosen to use this figure because it doesn't show the level of pollutants, but there is another figure I have. If I show you, it's just so ugly, so much pollutant. All this region, all the farmers, industries, whatever they are doing, they are finally coming to the Atlantic Ocean. Not many people know that, but it's really horrible. If it happens in US, you can, with lots of laws and all that are in place, you can imagine what's happening elsewhere. Okay, so we are screwing up environment like anything. Unless you are forced to see those, then you will see, oh, maybe we shouldn't do that much, but it's just horrible. So they have commissioned this, I think in 98 or something around slightly before that, started to model each of these places, what they do, and then what kind of fertilizers they use, and then remedies. So there's something called BMP, Best Management Practices, which means what do you have to do? Like there in the land use, we convert some grassland with some other land or things like that. So similar things here. You put some cover crop, you put some fences, you put more soil, you plant some kind of grasses so that it has less erosion. All these treatments that you have to do. So now given a land, you decide maybe 50% of this I'm going to do this treatment, another 50% I'm going to do another. Sometimes there could be overlap. So each of these little area you see, we have to decide. So the number of variables is huge. If I take the whole Chesapeake Bay, it goes more than 1 million. But if you concentrate like this one we are concentrating, we have still about 5,000 or 6,000 variables. So it's a large scale problem. And what are the objectives? Okay, so we need to do some treatment, and it's not going to happen in 1 year. So it's always a 5-year thing. So you say, how much money do I need for 5-year treatment of this? So cost is one thing you want to minimize. Second thing is how much pollution I'm putting. Like I've been talking to you about cost versus pollution, the whole idea coming from here. So here is my cost, and here is my nitrogen that I'm throwing on the atmosphere through this water body. That's why it's called watershed. All we find are Pareto solutions. You see like this. We find Pareto solutions here that says if you spend little money, you are throwing a lot of nitrogen. If you spend more money, you can throw less nitrogen. But I am not telling them what to do exactly. I am giving them maybe 10, 20 different solutions. You decide how much money you can spend. You can actually see if I spend from here this much more, I can reduce this much of pollution. All the C is in front of them. And now they can make a plan. This year what to do, next year we'll do it again and what to do. So here is an example when we solve this large scale problem with NSGA2. Eventually we went into NSGA3. We got just showing these 3 solutions and how what you have to do in each of this place we concentrated first, what you have to do. Then we've done transfer learning. It so happens that if you do something, you optimize for this region, let's say, and this is more rural. You come this part of it, very similar landscape. Whatever optimization results you find, that means what PMP to put where, you can actually transfer it there. So this is another way of optimizing at some place, taking the results and showing it to a similar place. I think Professor Ramu and his students yesterday was presenting me. They are also doing similar things here with transfer learning, identifying equivalence or similarity between objective functions or problems, and the results of one optimization can be transferred to the other. These are also some latest techniques in optimization people use. So this is a 6-year project. We are at our 5th year now. We've already given them the code and they are running it and using it. Next 2 years, we are going to do a lot of advanced stuff like surrogate based to make things faster. One run, our case takes about half a day. So they pick a place, they choose and fire it. So I say run optimization. Now they can go back and do their work, and they get a nice little email at the end saying your results are ready, and then they go and see. Okay, because sometimes you have to do this way. Here we don't have our own objective functions defined. It's their evaluation code, like they're developing since 1998. We have our optimization algorithm. We call for evaluating their code, and we get the result from there. So that calling, okay, these are government people. I'm probably same here too, but they don't let you touch their system. So they have a very secure system where they keep changing things. So we said, yeah, we are going to use only for evaluation purposes. We send the solution of BMP. All we need from you is what are the nitrogen level, phosphorus level, sediment level, and the cost. They said, no, you cannot call us directly. So we said, how? He said, you prepare a file and we'll read the file and we'll write our output in a file, and then you read the output file. This is like old fashioned. Even today we are doing the same way because they don't allow it. So what we do is we have a new GA solution, an offspring solution created. We want it to get evaluated. We don't have a F1, F2 function like I'm giving you. We have to call their code. First we do is create a file, and we send a ping to that code that a file is waiting. Whenever it's ready, it reads the file, it runs it, it takes few minutes, and then it saves it into another file, and a ping comes to our code saying it's ready. Now we go and read and extract the nitrogen, whatever information we need. So this read writing business take time, taking us to half a day to sometimes almost the full day if it's a bigger area. When you go to the whole Chesapeake Bay, that's our goal in 2 years to go. I think it's probably going to take 3-4 days to make one run. Okay, but that's probably okay for them because they will do this like once a year, once every 6 months. So they can wait 2-3 days. Okay, but even now, today, there are these security issues that we cannot overcome, and we have to be ready to do this kind of file-based optimization. We are doing multi-objective, we are doing decision making and everything here. Okay, I think I'm going to stop now. This is another engineering design problem with the engine design with 6 objectives we recently did. And there are these 6 objectives as you see. Their goal was to minimize the weight by 10 kilos. So their current design had 184 kilo. They said only goal for you is to reduce the weight by 10 kilos. And then they keep adding stuff. They said, okay, here there are 5 more objectives. It's a huge problem, you see, 145 variable, 146 constraints, 6 objectives. On top of it, they are all discrete, all the values. And we are able to give them about 100 engine designs with less than 174 kilo. So not only one, but 100 of them. Then, of course, here is the best one, but here are others. Then they come up with all kinds of things. They say, can you give us 2 solutions that have almost similar weight, but they look different? So from this we identify these 2 red line having the same weight, but other objectives different means they are different looking. Okay, so these are unconventional optimization you have to do when you are dealing with industry people. But yeah, we are always accepting all that kind of things.